let's consider an orbit that's not circular, which is common with most things in space. Some are very close to circular, but there's many things that are not circular, very elliptical. And basically, you have some object that's the center, and you have elliptical orbits with one of the foci at the center of that gravitating object. So this would be maybe a small satellite orbiting the moon or Earth or the sun or Jupiter. Okay. Now, the laws of physics hold for that system, just like they hold for swinging a ball around on a string and other laws. Newton's laws all apply. Conservation laws all apply. And so some that apply are that the mechanical energy is conserved. Okay, there's no external. If we choose both objects in our system, that means the mechanical energy is conserved. So we say delta E mechanical equals 0. Okay. Momentum's conserved. Okay, so we can say that delta P of the system equals 0. And also angular momentum is conserved. So we say delta L of the system equals 0. And I should put vector signs over those last two because they're whole vector form. Okay. Now, those three laws are all observed by the motion of these things. Okay. Now, if you do something, for example, you have thrusters on this object, then you can change these quantities because you'd import a work that was not part of the system. It would be external work. Okay. You'd be applying forces that would change the momentum of the system, and you could be applying torques that would change the angular momentum of the system. Okay. And I want to look at these things and see how we can build those up to find out how would you go from one close circular orbit to a far big circular orbit. Okay. All right. Now the thing about angular momentum is that it is equal to r cross p. R is the distance from some pivot point or some point we're referencing, our reference point, to where the object is moving. Okay, so we generally, it's wise to choose the center of the gravitating object as our reference point. And so R would be that. Now P would be tangent to the trajectory because it's in the direction of the velocity. And so when I think about r cross p, I'd need this angle here. So this would be rp sine of that angle which I indicate there. And then a direction given by the right-hand rule. Okay, so our right-hand rule would be r is pointing that way, p is pointing this way, which is there causes this to be the plane, which means our angular momentum is up. Or in other words, it's curling this way. So my thumb points up, it's curling this way, which we can see. It's curling counterclockwise. Okay. Now there are 2 points where this becomes very useful. One is right here. I'm going to call that R1. The other one is right here. I'll call that R2. And that's supposed to be at the very, very end where it starts to turn around. Okay. Now those points, the momenta are perfectly perpendicular to r because they're tangent to the circle and it's a turning point. So our r vector is perpendicular to the trajectory. Okay, and so that means that our angular momentum is rp or rmv. Okay, but if it's conserved, if we can say it's conserved, that means that R1 mv1 equals R2 mv2. Okay, the m's cancel, and that gives us a constrained relationship between the velocity here and the velocity here. Now, notably, since R2 is bigger than R1, that means V2 must be smaller than V1. And that's indeed what we see with satellites, is they usually are swooping around the gravitating object really fast, and they slow down and almost crawl out here, and then they come in faster and faster and faster and swoop around, and they go out here. And that's actually Kepler's second law. Okay, that the objects kind of sweep out equal areas in equal times. So it's moving super fast here, and so it creates a bigger kind of swath in the pie. It's moving super slow here, so it's a smaller swath in the pie, but it's longer, so you get the same area. And you can derive that from conservation of momentum, which I'm going to leave to the text. Okay, but what becomes useful is we have, at these 2 points, we have a constrained relationship. We can say that V2 equals V1 R1 over R2. Okay, that's one relationship we have. Okay, now with that, and combining it with conservation of energy, we can figure out how a spaceship would need to boost itself to get from a low circular orbit to a larger circular orbit. What's cool, it takes a lot of math, and you can derive this using those 2 equations. It's fairly complicated, but you can derive it. But you can also just go back to say, well, what's the overall orbital energy difference from the 2 orbits, given that the velocity and the orbital radius is constrained? Okay, so I just want to qualitatively point out how to think about that. So let's say here's our object here. Okay. And this is a planet, and our spaceship or satellite is in a circular orbit with a low altitude, and it wants to end up in a circular orbit with a big altitude. Okay, so this would be R1. Okay, and this would be R2. So when it's here. Okay. When it's here, it's got some velocity that's governed by our relationship we saw, which I'm going to write it as the square. V squared equals G big M over R. Okay. Remember, that's the relationship, how they're constrained if in a circular orbit. And so the bigger orbit has a smaller velocity. Okay. Now, how would you get out there? Now, what's cool about it is what we do is we wouldn't try and push ourselves out this way. Okay? What we'd actually do is just give ourselves a boost right here. We're going to apply a force over a small time interval, giving us a delta P right there. So we speed up. Now, if we speed up, that means this got bigger. Okay? And then this is no longer going to be true. We're not going to be in a circular orbit anymore. So remember, this was for circular orbits. But what it does is it puts me, now I get to follow this. This is true no matter what orbit. And I'm going to be in an elliptical orbit that puts me out to here. Okay. So I give myself a delta P just enough using my relationship here, figure out what speed I need so that when I get out here at this distance R, I am now tangent to this circular curve. Okay? But what you'll find is by using these, the velocity you have out here is super small. Remember, you're super fast here and you slow down out here. Okay? But it's not the right speed for this. It's actually too small for this one because otherwise I'd come back in. So I need to speed up even more to get into this orbit. So you give yourself another delta P. Okay? And I'll put a 1 and a 2 here because they're different. They're different values. And this delta P will give you the boost to get in this elliptical orbit, but you slow down by the time you get out here, and you have to give yourself another boost to speed back up to get into this big orbit. And that's how they would make an orbital change. Okay. And what's cool is you can derive how much change of momentum you'd get here and here by simply using these 2 rules. Okay, this conservation of momentum. Conservation of angular momentum and conservation of energy. Okay. Now the math is kind of complicated. It's pretty straightforward, but it's a lot. You have to do about a page worth of math to get that. But the point I want to emphasize is how would you do it, and that these 2 laws which we're familiar with are enough to get us to do it. And that's how NASA will boost satellites out in space.